Hello, everyone. In this short video, I want to talk about my research project, which is essentially tackling a problem of exploring for target search and rescue and for vegetation detection with a drone under power constraint. Especially, we are interested in the problems with the sparse goal distribution. That's why we employed a reinforcement learning algorithm to integrate the performance of the perception module and the constraints from power module to come up with an efficient pathing that maximizes the performance. In short, if we think about the problem with four waypoints, say that we have different goal objects. We see in practice that wind plays the most vital role. So essentially, you would want always to leverage wind to hit the targets that wind is helping you in their direction. And what really matters is that sometimes, for example, detection of oil spills on a lake, there is no target distribution known beforehand. So in such problem, it is very important that you just take into account the performance of your camera and push it to the edge, and as long as you're under your power constraint, you're using minimum amount of power. And for that, I used this reinforcement learning framework and treated the environments with sensory information as a simulation environment as my test environment, and tried to come up with a policy that maximizes the rewards per episode, which would constitute with the path with most amount of objects detected with least amount of power consumed. So in summary, if you look at the state of the art in this problem, right now, if the commercial drones essentially perform an image stitching, for this task, you perform an image stitching to find these objects on the lake in the aftermath. However, if we employ the Q-learning method in 2D and in 3D, we can show that with a significantly less amount of steps, you can essentially detect relatively a similar amount of objects. And another important thing is that the time duration is going to be significantly lower as well, as we can see soon. So this is how the network structure works. So for every target search domain, we take the target domain and break it down to a grid world. Every point in this grid is a state in addition to the different wind intensities that constitute our state space as well. Every state action transition that essentially will have a reward based on the power that you consumed and the essential objects that you detected. So if you want to go through the flowchart, essentially you have you get the target search domain, break it down to its state space. Initially, it's probably blank. And for each state action transition, it will have a meaning as a actual coordinate change into the simulation environment. I implemented this in Unreal Engine and gaming environment that will mimic the image streams through a photorealistic manner as well. So when you make a move with your drone, I essentially make a call to the environment, simulation environment, the agent moves and the image stream comes back to us. We can use different object detection algorithms. Here, YOLO v5, and even for a simple color segmentation problem, we can detect the objects and report the rewards to high-level RL planner. At the same time, the punishment, essentially the negative rewards from the cost of each action, they get translated here as well. One thing that I like to point out is that in theory, you can always fill in all these state action values, all these values, transition values. But as the state space grows, coming up with an optimal path will be a harder objective. However, it is important to note that the actual optimal path is not what we are necessarily interested in, because learning to that perfection is not actually representative of the performance of the system. Our goal is to, for any randomized goal distribution to have a initial essentially value matrix that dictates maximum amount of area essentially covered with a given limited battery life depending on the wind direction. So in this video, we actually can compare in terms of flight time. We can compare the two algorithms in terms of the flight time. And I solved it for harmful algae blooms on a lake. That you have a lake with high intensity in wind intensity on the left. We see the path that does the full complete coverage, although it is an energy aware from the state of the art literature that adjusts the speed of this drone based on the wind, so that at least it's minimizes the amount of power consumed with respect to speed. But as you see, 1 minute and 30 seconds for the 2D integrated path compared to around 3 minutes for the complete coverage, which kind of is expected. Now, if we expand the space and allow 3D decision makings as well, we see that the overall amount of traverse time is going to be significantly lower. And all these videos were on 7 times faster the actual speed. To end with, if you want to talk about the limitation of this work, is well, something that comes to your mind is curse of dimensionality. For every Q-learning based problem solving, we may have this problem, and the goal is to when you deploy to an, which leads me to the second problem that we are working on right now. When you want to transfer the policy that you develop from the simulation into the real world, it gives you a very good point to initialize your first searches. And at the same time, the algorithm is adaptive. So we are working on improving the generalizability of the work, so that essentially, if you assume that in a simulation through the fluid dynamics simulation that we did, that you spend a certain amount of power, if in reality it increased, essentially it would be translated in your reward formulation. And finally, we are trying to employ collision avoidance so that we can have a publicly acceptable framework working for outdoor environments. And here are our contact numbers. Thanks very much for watching this video.